Am I mirrored? Hi everyone, how's it going? See, people are slowly starting to trickle in. Hi Nicholas, how are you? I guess are you the moderator? Yeah, it looks like that. So thank you all so much for organizing it and inviting me back. Let's see. Are we starting on U of T time or are we starting on like regular person, real world time of actually starting on time? Let's switch back to webcam while we're waiting, I guess. Am I going transparent? I'm honestly a little bit impressed that people are up already, although I guess some of you might still be up from last night. Oh, opposite time zones. Yeah. Yeah, no, I guess like since this year Hack the Valley is virtual, it's a little bit more complicated. Like the whole idea of like this being a virtual hackathon is still a bit weird. Like you're not all sitting in some room over in the instructional center, like hiding away, hacking over things 24 hours. We're going to eat pizza. Well, those look sort of like more people are in the Toronto time zone. Discord activity has been pretty sparse the last half hour or so. Hi, Sarthak. I'm glad you made it this early in the morning. See, I guess people are trickling in. That's pretty exciting. Ah, okay. Up to me. Make another announcement at 9. Oh, actually 6 in the evening. Yeah, I need to get you. Even after 2 years of pandemic, I'm still not entirely used to the idea that, like, I'm used to the idea of doing things over Zoom or over Hopin or whatever other platform. The thing that really trips me up is just like what time of day it is for both me and for other people. Like it's so easy for me to forget. Like, wait, is today Saturday? Huh, that's kind of cool. Okay, yeah. So I'll probably start a little bit after 9 then. I might not wait until 9:10 sharp, since I assume you all normally get a lot of people from, well, not U of T, and I also presume that that number is probably higher this year, even because no one has to travel. Two requests in the queue. There's a little message that says 2 requests in the queue in the bottom right of my screen. Is that something I need to deal with, or is that something you all are going to deal with? Oh. Attendees can ask to share audio and video. Up to you if you'd like that. Oh, huh. Well, do I just click the big green plus button? I wasn't sure what exactly that meant, but yeah, sure. Why not? I don't know what just happened, but I clicked some big green buttons. So hopefully everything went well. Oh, random other note. By the way, my name is slightly wrong on the announcements. It's not William Yun. It's just Yun William Yu. Not a big deal, but happens pretty often. So yeah, it's really not a big deal. This happens so often that I've stopped worrying about it. I think it might have been wrong 2 years ago as well, the last time I gave this workshop. Oh well. Let's see. Okay, almost there. More people are trickling in. So where are y'all like coming from? Like I know people mentioned like they're in very different time zones right now, but like I assume that means you guys aren't in Toronto. Oh, all the way over in India. Oh, Toronto. Go Toronto. I figured that since this is a hackathon, I'm supposed to be wearing my sponsor gear, and like I'm being sponsored by the University of Toronto, so. Indonesia. Yeah, no, like the computer mathematical sciences is one of the main sponsors of this, and so clearly we have to have like all of our CMS reps wearing our gear. Although I actually don't have a CMS T-shirt. Like that's actually something I should get at some point. I just like haven't got one of those. Like I have a U of T Scarborough T-shirt, but I think I actually have a U of T Computer Science T-shirt somewhere as well as maybe U of T Math somewhere. But I definitely don't have a U of T CMS T-shirt. So clearly not doing my full duty as a hackathon sponsor. Maybe I'll try to remember to remedy that for next time. Is this session yes, it is an hour long. So the way it's going to work is I have a PowerPoint and I have a Google Colab. So I'm actually going to be switching between the two, and we're going to implement a couple of basic sketches, as well as go through some of the theory behind what it is. Like, I mean, nothing in too much detail since this is a hour-long hackathon workshop. But hopefully by the end of it, you'll have some sense of the possibilities that you can with these kinds of techniques. Like I think it said in the abstract, it's kind of magic. Weird stuff happens when you use random numbers, is basically the key point. Okay, so it's 9 o'clock, but I will wait a couple more minutes for people to trickle in. One year into programming and hackathons still sometimes confuse you. Well, if you're only 1 year into programming, that means the only hackathons you've probably been to have been virtual. I do think that it's just more of an experience when you're there in person. And yes, there are plenty of really good reasons why we haven't been having hackathons in person, of course, as I'm sure no one needs a reminder. But yeah, like it is just a very different feel. And how you run the hackathon or really any event online is something that a lot of people myself included, still don't do great. Like, certainly for like teaching classes, like I've had to learn so much about. I mean, I never thought I'd become an OBS streamer, and yet here I am. So. Let's see. Yeah, let's give it a couple more minutes. So, hi everyone, the people trickling in. I'm probably going to start around, let's say, 5 after-ish, maybe a give or take. So not quite UFT time, but just giving the people a little bit of time to trickle in, especially for those of you who are coming in from Toronto and for whom this is 9 a.m. bright and early, which is earlier than I prefer to teach classes at the very least. Oh, Discord announcement. I should like that. Yeah, no, sad face. I mean, I'm in Toronto, but you guys can't see because I have a fancy green screen, but I'm in my bedroom. So, like, it's also not as exciting as if I were over in IC, like actually giving this talk in person. Okay, a couple more people trickling in. Yep. Yeah, how are everyone's apps going? Or I assume most people are doing apps. Like, I don't know that for sure, but like, how are people's projects going? I guess you guys are, I guess not quite halfway, probably a third of the way through in terms of like raw hours, or maybe near to halfway. So it's always hard to count hackathon hours because, like, do you really count time that you need for sleeping? Like, you really should, but on the other hand, like, when do you sleep during a hackathon? That's always one of those open questions, right? Well, I mean, it always is brutal figuring out new stuff, but worthwhile. Or at least that's what I'm supposed to say as a professor. Otherwise, I'd be out of a job. I know that's one of the good things about hackathons being in person is that usually the hackathon organizers are pretty good about trying to make sure there's some amount of food around. There's just food floating around, which there obviously isn't when you're doing this online. Let's wait another minute or two. Looks like we are getting a slightly bigger crowd. And then we'll get started and start talking about the magic of hash functions. And so, let's see. Anything else on the Discord? Nope. And let's see. Oh, is there a separate Q&A from chat? Well, that's kind of interesting. I guess that sort of makes sense. At least that's sort of like what Zoom does as well. This platform seems better than some of the other platforms I've done like online workshops on. Okay, so it's now 5 after, and I figured we might as well go ahead and get started. And I know people might still be trickling in, but there's a lot of really cool stuff to cover, and I want to make sure we have enough time for questions. So please do just drop your questions in the chat or in the Q&A, and I'll be paying attention to that as I go through the presentation. So now, what am I going to talk about today? I'm talking about sketching algorithms, the magic of hash functions. And this is a workshop that I also ran in the last Hack the Valley back in, I want to say, January 2020. Time is weird. But yeah, so if you want, I will be spending half of my time on this PowerPoint to sort of explain the basics of sketching algorithms and why they're so cool. And the other half of my time will actually go into a Google Colab and we'll implement some of these. And so I really want to drive home the point that these are all well, many of these data structures there already are packages for, but even if there aren't packages for them, they're all really easy to implement and sometimes can give you significant savings in time and space. And they're not super difficult. So I will actually be, I mean, I have a little script for myself already, but I will actually be typing out the Python code for it live. So with that, what am I talking about? So what are sketching algorithms? What are hash functions? Well, hopefully many of you have heard of hash functions, but sketching algorithms are these sublinear space algorithms. They're a family of algorithms representing really, really big data as these small probabilistic summaries. And the key here is that the sort of weird super lossy compression allows you to still like estimate interesting quantities that you care about, like the cardinality of a set. So like if you have a big data set, how many people have you seen in total while deduplicating for non-unique entries? Or things like quantiles, frequency distributions, set membership, what's the majority element if you have, if you're receiving a, or things like, and these are widely used in routers, databases, search, etc. So for example, if you are a router, or let's say you're a firewall sitting between a network and the internet. And one of the things you might want to ask is, well, what are all the IP addresses that are hitting the firewall? Like maybe you're undergoing some sort of DDoS attack and you want to put in the firewall rule for all the most common IP addresses. But of course, there's so many requests coming in that you can't store all of the IP addresses on like the limited space you have. And so instead, you might use a sketch to just store the most common ones. The other super cool thing about sketches is that they compose. So let's assume we have some data stream that's flowing in. And what happens when you have this big data stream flowing in is you start, as the data stream passes by your program, it starts creating a summary of it. So I have it represented here as this little box of zeros and ones, but it's just some small summary that updates as the stream goes by. But if you have one stream for, say, the total number of elements in the set, and you have another stream, let's say it's this is the set of some objects that have a property. So I work in computational biology, so I care about things like whether or not patients have hypertension. So I might have some property A that patients have hypertension, and I have some other sketch for whether or not patients have, say, diabetes. And one of the really cool things about sketches is that you can combine them together without having to regenerate everything. And that gives you properties A and B. So all the patients that have both patients and hypertension, or maybe patients or hypertension, depending on what kind of sketch you're exactly using. And so these turn out to be really useful in real life because you can answer these kinds of questions quickly without having to rerun through your entire data set. And they're also just very small, space efficient, and time efficient. And so basically the general idea is that sketches are these compressed summaries that you can compute on to save space and time. And well, what are some of the problems that we care about? So let's start with one of the simplest problems. This is the set membership problem. So given a stream of items, I want to know if I saw a particular item. And this is very common. So you might be like, well, I have a bunch of these database requests. And if I've seen a request before, maybe I want to just like look up and go into a pre-cached, pre-generated database and see if I already have the answer for that, as opposed to actually computing and finding that item. But now you might want a quick way of checking in memory if you've seen something before. And so there are a couple ways of doing this, but one way using sketches is to take all of your items, you hash them, and so how much space does this take? This takes the number of items times the hash size. So maybe that's, if you have a 64-bit hash, then maybe that's 64 divided by 8. So maybe that's an 8-byte hash, or maybe that's a 32-byte hash, depending on how big your hash size is. Sometimes you might truncate these, and assuming that you don't have too many items, you might still be able to truncate them and get a good sense of whether or not an item was seen before. So if you store a hash value and you see the same hash value again, with high likelihood, you actually did see that item. And there are other ways of doing this, such as like you can create some sort of bit string that represents all this data probabilistically. And so these are the sort of techniques that we'll be going through. Okay, with all of that, please drop any questions in the chat because I've been going through this quickly and I don't know everyone's backgrounds. But let's actually go to implementing a basic set membership query in a collab. So this will be just basically a warm-up exercise, since I will just be making use of existing algorithms in the Python standard library, basically. So going over to the collab. So in this workshop, we're going to see some common probabilistic data sketches. First, you need to set up your Python environment. So these are just some common libraries that I'll be using. The slide deck that I'm using is also available. But so now, ignoring the fact, so we're going to import a couple libraries. We're going to import this library here, Pimpler, is just going to allow us to measure how big our sketches are. So measures the size of a class and tells us whether or not we're actually saving space. Bitstring we're going to use for actually generating some of these sketches. And we also have this fast hashing library, which we're not going to use yet, but we'll get to in a moment when we start talking about the sketch-based methods for doing things. So now we have this problem of set membership, right? So given a stream of objects S1 through Sn, or S infinity if it's an infinite stream, at any point in the stream, we want to answer the question, have I seen a query object Q? Well, now, many of you have probably done a little bit of Python, and you'll recognize that Python already has a couple built-in data structures to do lists. And so let's make use of it, but let's create a new class just to encapsulate all of our knowledge. And then we'll show how we can augment these kinds of classes with different kinds of ways of counting. So let's go and get started. That was the wrong button. Okay. So for naive set membership, let's create a class. Let's call it naive set membership. You always need to remember your doc strings, so let's call this the naive method. And this will just stores all elements of the stream in a hash table or Python set. Okay, this is a Python class, so we'll initialize it. And within this Python class, we're going to store our data structure. And since we're just going to be using the Python built-in set, we're just going to call self.data is equal to set. And we have some update operations. So when we add an element to the set, what are we going to do? Self.data .update x. Okay. And we can also define a new query, which is, does our set contain this item? And then we'll return q in self.data. And once we've done this, it's pretty easy to, use our data structure. So let's initialize a copy of our data structure. A is equal to naive set membership, if I can spell correctly. And then for I in range, let's say 0 to 10,000 minus the 9,999, we're going to say a.update I. So it's going to add all these items to the set. And notice that seeing an item twice in the stream doesn't affect anything. So actually, let me do that in a moment. But we can test to see whether our particular item is in the stream. So let's say for I in range minus 10 to 10, we're going to print string I plus in a, and then we're going to say true or false. Is that string in A? And when you do this, well, you'll see, well, minus 10 is in A, 0 is in A, 1 is in A. Sorry, minus 10 is not in A. 0 is in A, 3 is in A, 5 is in A, 6 is in A. Notice that we can add an item twice, and it doesn't really make a difference. So for an I in range 10 to 10,000, you can update that, and it won't do anything because to the outputs. And this is even true if you have a slightly different range. So instead of going the second time, instead of adding from to 10,000, maybe add to 100,000. And you still get the correct answers because this is a data structure in Python that is explicitly storing every element of the set. But now, there's a bit of an issue with this, which is, how big is this? Well, we can print the size of this. So A has size, let's see, how many bytes? Well, we're going to measure the number of bytes, which is going to be A size of, that's why we imported this, A.data, because that's the data structure we're storing this all in. And when you do this, you find that A has size 7 million bytes. And if you increase the elements in your set, so if I go up to 1 million elements in your set, and all of a sudden A has size 65 million bytes. So this data structure works, and it works really, really well. And this is, whenever you're starting something, you don't want to prematurely optimize, and this is the correct way of starting to keep track of the elements in the set. but you might find that this doesn't scale with whatever application you care about. Which brings us then to other ways of doing probabilistic set membership by sketching. And so some of you who've taken upper level computer science classes might have heard of Bloom filters. And so this is sort of the baby's first sketch. So this is one of the first sketches that you might encounter. And basically the way it works is it uses the magic of hash functions generally not colliding or colliding with very low probability to allow you to figure out whether an item is in your set. So what we do here is we have a modified bit string and we have multiple hash functions. So when an item is inserted, we set all of the hash bits and not just one of them. So when this X is inserted over here, we put it here, we put a 1 there, a 1 there, and the 1 there, all at the same time. And so when each item, because we have 3 different hash functions, and then we map it to each of those hash functions individually. And then obviously, if you had inserted an item in, then all of the bits corresponding to the hash locations of that item will be 1. If you didn't insert the item, then with some high likelihood, they won't all be 1. And so this way you know whether or not an item was probably inserted. And this actually gives you pretty significant space savings. You get the possibility of false positives if you insert too many items in, but it's unlikely given the right choice of the number of hash functions. So, well, let's jump back to the Colab and implement a Bloom filter, which we just described. So we're basically going to make use of a bit vector, and we're going to have a bunch of different hash functions that map to different locations in this bit string, and that's how we're going to test whether or not the item is actually in there. So, well, how are we going to start? Well, let's go ahead and go up, and we can just copy some of our code here. So the boilerplate code is all going to be the same, though we're going to rename it. So I'm going to copy the boilerplate here. I'm going to name this a Bloom filter. So note that Bloom filters are actually pretty common, and there exist already Python Bloom filters. But let's go ahead and implement it so you see what it's like. So this probabilistically answers set membership queries. It will never give false negatives. Let's say if Q is in set, will answer true, but may give false positives. So let's say sometimes will answer true, even if not in set. Which is a bit of a bummer, but often this is an all right trade-off. So we have a slightly different data structure. So the first thing we're going to do is I'm going to make life easier for ourselves. And let's say we're going to have initializing. We're going to have a couple initialization parameters. So how big is our data structure? So instead of our data structure expanding with the number of items in our set, we specify a maximum size for it at the beginning. And I'm going to specify 2 to the 17 bits. So 2 to the 11 bytes, so about 2,000 bytes, roughly speaking. And I'm going to say that we have, say, 10 hashes to start out. And those are going to be my default initialization parameters. I'm going to make life a bit easier for myself and assert that size in bits is less than 2 to the 32, because when you start having way too big of a data structure, things can go weird in terms of memory usage. And well, let's actually define our data structure. So it's just going to be a big bit string. So this is a big bit string, which we imported a little bit ago. So we're going to initialize a big bit string, so a big string of zeros. Well, let's also define the size. It's just the size in bits. And let's say the number of hash functions. Number of hash functions, well, that's part of our initialization parameter. We're just storing all these parameters inside of our data structure itself. And then now the update is going to be a little bit weird, because instead of just adding it to this object, we're going to have to set to true a bunch of locations in our bit string. What are all the locations that are in a bit string we need to set to true? Well, we also had imported this hash function, this fast hashing library, and so we're going to make use of it. So murmur hash3.hash, and well, let's say we're going to turn each of our items that we insert into a string just to make hashing work a little bit better. And we're going to have some random seed, which we're going to call I. We haven't defined I yet, but this is just the random seed so that we can identify each of our different hash functions. So in our particular case, I will go from 0 to 9 because, well, you have your first hash function, you have your second hash function, third, and so on. So we have all these different hash functions. And then we need, once we hash it, then we need to fit it into turn it into a location in our bit string. So we're just going to take a mod of it with the size. And the key here is that we're going to do this for every single I, for I in our range, self.num hash. Let's see. Okay, and so we're going to add it into every one of these locations whenever we enter an item. And the next thing we're going to do is we're going to, whenever we check to see if an item is in our Bloom filter, we're going to do the same thing, except we're just going to check all those different locations. So we're going to check if all of these locations are true. And this is the same set of locations that we looked at, that we inserted into. And that's a Bloom filter. So about a dozen lines of, not even a dozen lines of code. And now we have a working Bloom filter. So let's test it out. So, well, let's say that A is equal to a Bloom filter. And let's do the same thing that we did earlier. So let's say for I in range from 0 to 9,999, what we're going to do is we're going to add it in, and we'll see if our answer is correct. So let's print out all of this. I think I also need, for a size, I also need a dot bytes there. So now we're going to do the same thing, except, oh, what happened? Self.size. Oh, I missed the dot, didn't I? Assert size in bits. Size in bits. Oh, what else did I do now? So x is not defined. String of s. Oh, I called it q. Well, that's what happens when you change your variable names. Okay, so note that A has size only 16,000 bytes, and it's giving us the same responses. So all these negative numbers are not in their set. All these positive numbers are in their set, which is good. But now, sometimes weird stuff can happen. So for example, if you start having a lot more items in your set, so maybe if we add in a bunch more items, let's say up 10 to the 5 in numbers instead, well, then things go badly. Because now all of a sudden we filled up all the locations in our bit vector, and so now our data structure is answering true for everything, which is not so good. If we only had some intermediate amount, say 2 times 10 to the 4th, you see what's sort of going on, which is as you enter more items into your data structure, you have the possibility of false positives keeps on increasing. And so if we have 20,000 items in our set, then most of the time when you have an item that's not in your set, you do answer false, which is correct. But occasionally you have these false positives here, which are not so good. And this is the price you pay for having a data structure that's only 16,000 bytes, as opposed to 65,000 bytes. So you save a lot of space, but occasionally things go wrong. Okay, let's see. Any questions in chat? No, doesn't look like it. So you guys now know what probabilistic data structures are. And now, if this were a graduate class in data structures, or even an upper-level undergrad class in data structures, I would spend a lot of time going through all the mathematics of why Bloom filters work. Actually, if it was a graduate-level class, I'd probably skip over that and skip the more interesting sketches. But regardless, we do a lot more analysis. But since this is a hackathon workshop, all we're doing is we're giving you these tools and giving you a hint that these are the things that you can do with the magic of hash functions. And one of the nice things is there have been a lot of brilliant computer scientists and mathematicians who've spent a lot of time coming up with these data structures. And so all you have to do is, well, sometimes you can just import them or pip install them. Other times, as you can see, many of these data structures are actually pretty easy to implement. And we'll see a couple more implementations of data structures, and that it's really not that scary. Like you're usually implementable in a couple dozen lines of code. So let's talk about a different problem, which is a little bit more interesting than just set membership. So let's ask the question of how many distinct items exist in the set. So maybe you have some data stream and you want to know the total number of unique suggestions in some sort of suggestion box, but you have someone who's spamming the chat with F constantly. And now you don't want to count whenever people are just spamming the chat. And so the question is, how do you figure out the unique subset of this set of chat messages you've been receiving? Well, it turns out this is something you can do using sketches as well. So this relies on a very important fact about hash functions, which is that hash functions behave almost randomly. So whenever you see a hash, whenever you hash a value, it sort of randomly gets moved to somewhere in your range. And so now let's imagine that our range is somewhere between 0 and 1. So now in real life, most hash functions are going to go between 0 and 2 to the 32 because you're hashing to a 32-bit number or 2 to the 64. But you can normalize that and just divide it out, and you can think of it as hashing between 0 and 1. And now, if you have two random numbers between 0 and 1, it turns out that in expectation, so this is a fancy mathematical term for those of you who don't know, for sort of the typical behavior. So the typical behavior is for the minimum of those two items to be about a third of the way in, as you can sort of see, because at around a third of the, because if they were evenly spaced, they'd be at a third and 2/3. And it turns out when you have more and more items, when you have 3 items, then the typical behavior is for the minimum of these numbers to be about a fourth. And when you have 9 items, the typical behavior is for the minimum of the items to be about 1/10. And the expected minimum is therefore about 1 over n plus 1. If this were a math class, we would actually make use of probability distribution functions and compute this. But this isn't a math class, and so you'll have to take my word for it. Or you could run it experimentally. It's pretty easy to see. So how much storage do we need for this? Well, it's about 1 over n plus 1, so you need about O of log n bits of storage to store just the minimum, instead of storing all the distinct items in the list. Now, of course, if you just do this once, it doesn't work so well, because if you just do it once, well, you have a big amount of error. But if you do this 10,000 times, this gives you a good estimator, and then you can just take the average, and it gives you about 1% error, which is the key behind many of these sketches, is you take some estimator that by itself has some big error, and you just repeat it a bunch of times, and then that decreases your error. But yeah, so it turns out you can even do better than this. So there are some super fancy techniques, which we won't get into, where instead of storing the minimum item, you take all these objects in your set, you hash them, and then you take the minimum, you hash them, you take the minimum value, and then you only store the number of 0 bits before the first one. And it turns out even that's enough information. So you only really need O of log n space. So these are really, really tiny data structures that really are efficient for really large databases. And what's more, just like with Bloom filters and with these other sketches, you can combine them. So if you have hyperlog sketches, you can combine them to find the union cardinality, so the size of the union of multiple sets. And you can also use these to figure out the size of the intersection, because if you have a union of 2 hyperlog operations, well, all you have to do is you have to take the maximum of each of these sketches, and they merge together losslessly. The intersection isn't quite lossless, because you're making use of just some set properties, but you can still do it. There are other sketches which let you do even better, like the min-hash sketch for Jacquard index. So basically, you want to measure the similarity between 2 sets, which is the size of the intersection divided by the size of the union. Well, this was a problem that people had, people in tech actually have. I don't know how many of you are old enough to remember Alta Vista. My guess is that very few of you have heard of Alta Vista, but hopefully many of you have heard of a company called Google. So now, Alta Vista, back in the day, was one of the big search engines. They eventually got killed because, well, their competitors, like Google, ended up just being better. But at the time, people at Alta Vista, so Andre Broder, was trying to figure out how you deduplicate websites. So like, if you look online and you search for something, there might be a bunch of copies of Wikipedia floating around, and you don't want to return 10 copies of Wikipedia, because that's not interesting to someone who's searching for data. But how do you deduplicate when there might be slight variations? And his idea was, well, you just look at the sets of words, the sets of phrases in each of these web pages, and if the sets overlap too much, well, then that probably means they're duplicates. But now, storing in all these sets of words is really time-consuming, or is really space-consuming. So instead, what you do is you imagine some random permutation of all these sets. So let's say set A is all the sets of words in website A, and set B is all the sets of words in website B. And these gray boxes here in the middle are the intersection between the two. If you think of a random permutation of all these items, well, there's some chance that the first items are the same. So in both sets. So basically, we're taking the minimum item in set A and the minimum item in set B, and occasionally they'll match. So occasionally that minimum item will be a gray item. And the chance of that is, of course, exactly the size of the minimum divided by the size of all the items. And this gives you the Jacquard index. And so what this means is that if you can randomly permute your elements, well, then you can find the Jacquard index, because you can just do these random permutations several times, and you get these empirical probabilities. It turns out that instead of using permutations, because those are expensive, we're going to use hash functions. So it takes log n bits. And you store the minimum hash for each of the sets A and B, and sometimes those hashes will be the same. And when they are, well, that tells you an estimate for the Jaccard index, so how similar two different sets are. Let me work through an example quickly because I'm speeding through this, and hopefully you guys are keeping up. Please do stop me if there are any questions. So now, in the worked example, let's say we have 7 buckets. So we have, say, A, which has 5 million items. We take 7 hash values of it, and I've written these out here. And you have some other set B that has 10 million hash items. And then 10 million items. You take the hashes of all those items, and you take the minimums. So there are 7 different hash functions. So this is hash 1, this is hash 2, and so on through hash 7. And you're applying this to all 5 million items or all 10 million items. But now all you have to do is you compare these. Come on. And occasionally they'll be equal. And you can estimate the overlap of the two sets by just how many times they're equal. So as an estimate, you can say the Jaccard index is about 2.7. And another nice property is, of course, you can also merge sketches to get the sketch of the union, just like you could with the hyperlog sketches. And you note that this sketch is actually very similar to the sketch that we did earlier for union cardinality. In fact, it's stored in exactly the same kind of space because all you're doing is you're storing the minimum of a hash value. And so by doing this, you're able to quickly figure out the set union and intersection cardinality type measurements. So like how similar are two sets, how much do they overlap, what's the total number of unique elements. You're able to do this approximately in much, much less space than you would need to if you stored the entire set. Let's jump back over to the Colab since I've been talking all this math and data structures, and let's actually see this in action. So let's go back to my Colab. And where am I? So we just did Bloom filters, and now let's do count distinct. So given a stream of objects, compute the number of distinct elements. Well, now we can do this with a set again. So if you go back up to our code for a set, well, naive set membership. Let's copy this. And let's call this naive count distinct. So this is not going to store all. So this is, again, it's just going to store all the elements of the stream in the hash table. We still have this contains operation. We're going to add a couple new operations. One of them is going to be count. So how many items are in it? Well, that's pretty easy, right? You just return the length of your set, so the size of your set. And so that gives you a length. This is pretty trivial. But since we're thinking about this as a probabilistic sketch, which is not really, because it's actually not a sketch at all, it's just your entire data, but you can think about adding together two different sets. So if you want to add together two sets, let's define an add operation. So you're going to add one copy of it to another. And what you're going to do is you're going to return, we're going to start by saying the result is equal to one copy. So, a new copy, naive count distinct. And then you're also going to have the result.data is going to be equal to self.data.union color.data. Because you're really just taking the union of these sets and then you return the result. And that gives you a naive way of counting the number of distinct items. It's naive because it's exact and just makes use of the Python set. So this is pretty easy. Let's see what happens. So let's say A is equal to naive count distinct. And for I in range 10 to the 4th, a.update I. And well, we can print the number of distinct items in their set. So print A has how many distinct elements? Let's see, format a.count. What happened here? I didn't have an I layer. For I in range, naive count distinct not defined. Oh, I misspelled distinct. Okay, A has 10,000 elements. This is great. And note that it doesn't matter if we see an item twice. So it still has 10,000 distinct items. But if you increase the number to like 10 to the 5, well, then it has more distinct items. And of course, we can measure the size of the set. It's going to be exactly the same size as the size of the other set because it's the exact same data structure as we used for naive set membership. So now it has 7 million bytes. If you increase it even more, well, obviously it's increasing with a number of elements in your set. So if you have 1 million distinct elements, then you need 65 million bytes, 65 megabytes. Megabytes? No, megabytes, not megabytes. Anyway, so this is the naive way of doing things. And this should be the first way you try because it works pretty well if you have a small data set. But if you have a really big data set, you might need to try something different. So, excuse me, sorry, talking too fast. Yeah, so if you have something that's slightly bigger, you might want to use something more clever. So this is the KMV set cardinality. It's basically making use of the idea that we did in the PowerPoint a little bit ago, where the number of items in the set determines the minimum value. And so if you store the minimum value, say 10,000 times, and then take the inverse of it, you get an estimate for the total size of your set. Now, there's going to be some amount of error, but we can accept that often. So let's go back to the collab. So KMV set cardinality. So this is going to be a little bit more complicated, but the first thing we're going to do is we're going to import NumPy because we're going to make use of some operations here. And let's call this class KMV, since that's just one of the names of the set. And this is going to be the K minimum values estimator. That's why we call it KMV. And it approximately answers number of distinct items in a data stream. We'll have error roughly 1 divided by the square root of the number of hashes. And this is just because you can think of each hash as an independent experiment. And so you're experimenting 10,000 times or 100 times or whatever. And then you're taking the average of all your results, and that gives you some lower amount of error. Let's end our doc string. So we can define an initialization. So we're going to initialize, and the key thing here is we're going to need to know the number of hash functions we're using. So that's going to be the number of minimum values we store. We're going to store the minimum value of the set under each of our hash functions. So self.data is going to be equal to, so I'm going to actually store this in a slightly different way because empty buckets are slightly different. So instead of storing zeros, I'm going to initialize this as a vector of -1s. D-type equals empty.uint32. And so you'll notice that I'm initializing these as -1s, but my type here is an unsigned integer. So as all of you will know who've worked with unsigned integers, basically what I'm meaning is that I'm overflowing. And so I'm storing the maximum possible unsigned 32-bit integer in each of these locations. Because what's going to happen later is when we're updating an item, we're going to take the minimum of what's currently in the set and the new hash function. And so if your data structure is initialized with zeros, well, that's not good because that's already the minimum value. And so you have to initialize it with the maximum value instead. And of course, we're storing the number of hash functions, num hash. And we're going to just do 100 for now. In practice, you might want to do more, but it'll depend on how much error you can tolerate. So now we have this data structure set up. So we have a vector of -1s, or a vector of, I don't remember what 2 to the 32 is, like 4 billion something. You have a vector of these. And then in order to update, we're going to take the minimum with each of these for each of the hash values. So this is our update operation. Self.data is going to be equal to empty.minimum. And note that this is a vector minimum. So this is going to take the minimum across both all the vectors in self.data with against all the vectors in this new that we get from this hash function. So again, we're going to use the murmur hash3 hash function. We're going to use the same thing, string of x, and I is going to determine which hash function. And let's say signed is equal to false because we're using unsigned ints here. For I in range self.num hash. Okay, so what are we doing? This line here is just updating the sketch by looking at the minimums of looking at the value that you get when you run the hash function on your new item. So you have 100 hash functions. You're applying them all to your new items. Let's say your new item is applesauce. So you're hashing applesauce 100 times. And for each of those times, you get some value. And then you check to see if that value is smaller than the number in the corresponding bucket in your hash structure. And when it is, you store you store the smaller of the two. And so this is why we initialized with the maximum value, because we want to ensure that initially you store just the correct element. You store whatever element is the first one you do. And with vanishing the small probability, you hit the maximum item. Okay, so now how do we count how many things are in our set? Now this is a little bit more complicated but you remember that the whole point of this analysis was that it's about the total number of items is about the inverse of the minimum item. But you have to do this many times, and so what we're going to do instead is we're going to take the inverse of the let's see, which one did I do? You're going to take the inverse of the average of the minimum items. So let's say we're going to return, well, by inverse, we're going to have to renormalize. So it's going to be, we're going to take 2 to the 32 divided by the mean, so the average of all the all the buckets. And it turns out that for complicated mathematical reasons, you have to subtract 1. If you're familiar with statistics, it's unsurprising that you occasionally have to subtract 1, but we're not going to go into detail about that. And well, let's see if this works. So A is equal to KMV. And for I in range 10 to the 4th, well, A dot update I. So we're going to add all these items in. And then we're going to ask how big is our data structure. So say print A has about, and this is approximate because things might go wrong. So A has about 0, let's see, let's only do 2 decimal places, distinct elements. Format A.count. So what happens? So we inserted 10,000 items, but our approximation is 10,365 items. And so this is the approximation error that we get. It's actually a little bit lower than our estimate, but of course, sometimes randomly it will be lower. So we had 100 hash functions, so you should expect about 10% error, so within about 1,000. And here we got error levels less than that. Now, seeing an item twice doesn't make a difference. So if you insert the same item multiple times, you're going to get the exact same result here. Now, of course, if you now one of the cool things though is you can also merge together sketches. So let's define that function. So let's say return add self and other. Well, oh wait, so we need to define add, not return add. So we're going to define our add function. And I'm going to assert that our 2 data structures have the same number of hash functions, because otherwise it's not defined how you merge together 2 sketches. It's going to equal other dot num hash. So, and then all you do is you take the result is equal to some new KMV estimator with the same number of hash functions. And then you're going to set the data structure, so our vector, to be the minimum of the vectors of both. And return that result. And so what this is going to allow us to do is this is going to allow us to add things together. So now let's suppose that we have, let's also print the size of this. So what is the size of this? 912 bytes. Is that correct? Yeah, it's close enough. So anyway, we can also create a new sketch. B is equal to KMV, a second one. And let's add in for I in range 10 times 10 to the 4th divided by 2 through 10 to the 4th divided by 2 plus 10 to the 4th. So what we're doing here is our first sketch here, A, is from 0 to 9,999. And this sketch here is from 0, let's see, from 4,999, or sorry, from 5,000 to 14,999, or something like that. So there's some amount of overlap, but it's not complete overlap. And B dot update I, and we can see how many items are in B. So let's say B has about how many items, and B has what size. So, wait a moment. What happened to B? Those estimates should. Oh, those estimates should not be exactly the same because I forgot to put in the right variable here. Okay, so B has a different number of items. The estimate is different, even though it's actually the same number of items. But importantly, we can now say C is equal to A plus B. And when you do this, you can print A union B has how many distinct items? Distinct elements. So this is C.count. So we just added these two together. And and you get about 15,000 distinct items. Let's do 2F there. You get about 15,000 distinct items. Oh, wait, what wrong? What went wrong? Invalid format specifier. I need a period here, don't I? Yeah, so 15,000 distinct items. So, and importantly, the size of our sketch. So if we print the size of c.data, the sketch size hasn't increased, even though we have more items here. The price you pay is this amount of error. And you can do the same thing. I am running a little bit low on time, so you can do the same thing for Jacquard index. I'm just going to copy and paste some of my code for that so that you have this available. Let's see. So this is naive Jacquard index. And so you can do it with sets. And so the Jacquard index between A and B is then going to be 0.333 because there are 5,000 elements in their overlap. And you can do the same thing. So what we did is we just initialized this as sets, and then we combined the Jacquard index is just the overlap of the two sets. And so you can just use a set intersection and return that value. But now for the KMB Jacquard estimator, so you can do the same thing, but instead we're going to have a new function and input it slightly differently. So you note that our new function is here. So this is the Jacquard index, and what you're doing is, well, you're using the same exact sketch, and now you're just comparing how many times the buckets are equal. So that's what we did in the PowerPoint over here. All we're doing is comparing the number of times all the buckets were equal, and then that gives us some estimate for the amount of overlap. And when you do that, what you end up getting is, well, let's run that. Hopefully all my code is correct. Let's do a .2f there. Yeah, so A has about 10,000 distinct elements, and it has size 2,000 bytes. Wait, why does it have 2,000 bytes? Oh, because I changed the number of hashes. I increased the number of hashes to 256. And B has about the same number of bytes, and you have this Jacquard index of 0.31. Now note that if you change the number of hashes to make it much smaller, you get a much bigger error. So well, that gives you 0.3. So that was actually pretty good. But let's say 5 hashes. Well, with 5 hashes, the Jacquard index that you get is actually pretty bad because you're only using 152 bytes, and you're getting some wildly wrong estimates. But if you increase it to some big number like 500, then all of a sudden your error gets pretty low. And that's the sort of key of this sort of probabilistic sketching, is that you can tune how big your data structure is by how many of these hash functions you're using, and that gives you the ability to store things in exactly as much space as you want by paying some price in the error. And the last thing I'm going to do is I'm going to show you an example of this in practice, which is we can run this sort of min-hash sketch on actual data. So let's say that we have some actual data. Let's see. I am going to, where am I going to pull this from? This is going to be a text comparison, and I'm going to pull some books from Project Gutenberg. So I'm going to, let's see. I'm going to start by just creating, so this is all just some setup to allow us to pull some books from Project Gutenberg. Next thing we're going to do is we're going to define a new sketch type, which is going to take a book and take all pairs of words or all groups of K words. If you're familiar with linguistics, you might or like natural language processing, these are probably called, you've probably heard of these as called n-grams. You're going to take all of those, we're going to call them shingos, and what this is going to do is it's going to create a set using this K minimum value estimator of all the sets of n-grams in your data set, and we can have a data set be just a book. So I'm a fan of of Faustus by Christopher Marlowe. So what we're going to do is we're going to create a sketch from the story of Faustus by Christopher Marlowe. And it's going to take a little bit of time because we just went to Project Gutenberg and downloaded this entire book. So this is this entire book. So we just downloaded this entire book, and we took all the different sets of n-grams in it, and we put them in a set, and then we created this min-hash sketch out of it. And let's also do this. I'm also a fan of Jane Austen, so let's do this for a couple other books. So let's say we do this for Pride and Prejudice That's for those of you who are unfamiliar, you've probably heard the beginning of Pride and Prejudice at least. So truth universally acknowledged that a single man in position of good fortune must be in want of a wife. Very ironically stated if you've actually read the book. But yeah, so you can do this for other books like Pride and Prejudice by Jane Austen, Sense and Sensibility by Jane Austen. And one question you might ask is, well, when I do this, which of these books are more similar to each other? Will the two Jane Austen books show up as more similar than the Christopher Marlowe book? And so we're going to create sketches of all these, and then we're going to analyze whether or not these actually are more similar. So we're creating min-hash sketches of each of these books, and then we're just going to take these min-hash sketches and look at their Jacquard similarity, and that's going to tell us how similar these books are. It's going to take a little bit of time because it is actually taking the entirety of each of these books and turning, oh, it's done. Well, anyway, so it's done. And now that we have that, so that took a little bit of time, but now we can actually do this much more quickly. So like, let's say Faust and Pride Jacquard similarity. So this Jacquard similarity between Dr. Faustus and Pride and Prejudice is going to be, Faust. So these are all KMV sketches. And so we're going to take the Jacquard index of Faust with Pride. When you do this, you find that the Jacquard similarity of these two books is about 0.08, which isn't that much. It basically means that about 8% of the 2 grams, so of the pairs of words in Faustus, are the same as the pairs of words in Pride and Prejudice. Well, let's take a look at what about Faust and Sense and Sensibility. Maybe that's a little bit higher. So if you do Sense and Sensibility instead, well, that's still not great, so 0.03, but that's sort of expected. But now the real question is what happens when you look at Pride and Prejudice and Sense and Sensibility. Are those more similar? So is one Jane Austen book more similar to another Jane Austen book than they are to Dr. Faustus? And the answer to that is yes. So you'll notice that when we do the same thing for Pride and Prejudice and Sense and Sensibility, the Jacquard index is much higher. And so you have a very quick way of figuring out the similarity between two different text, really long text documents by using these small probabilistic sketches. Importantly, if we look at what this is stored as, pride.data, what does that look like? That's just an array of 100 numbers. That's all we're storing. And from this, we're able to analyze the fact that Pride and Prejudice and Sense and Sensibility are more similar to each other than Dr. Faustus by Christopher Marlowe. And that's just by looking at this vector of 100 hash values. Now, this is also something that I've used in practice. So I used to be a postdoc at Harvard Medical School, and we did these same things for a big national claims database of patients. We wanted to actually use this to look at how many patients have diagnoses in some big database, how many people have diagnoses or medications and medications, hypertension and diabetes, and so on. And so you can do this exactly by just using effectively some sort of set-like data structure. And you can do this, but it takes a while. You'll notice that the performance of just using an SQL query, which is pretty optimized, on some of these bigger data sets, it can take quite a few seconds, on the order of 20 minutes for some of these queries. But, and your database size is also really big, so it's about 4 terabytes because you're storing all these medical records. But you can do a lot better if you make use of min-hash and hyperlog-log sketches. So the types of sketches we've just been describing, you can, the sketches are much, much faster. And in fact, they're almost constant time. They're all on the order of, milliseconds. And the database size is also decreased from 4 terabytes down to 5 gigabytes because you're only storing these, instead of storing the actual patient data, you're only storing these arrays of numbers. And, it turns out you do have some amount of error, but depending on how you can change the parameters to have different amounts of errors for different types of applications. And often you can accept a few % of error for the massive improvements in speed. So in conclusion, there are lots of pros and cons to the sketches. They make use of the magic of hash functions to give you a very small memory footprint when you're analyzing really massive data for some application. They're also composable, so they're good for parallel processing or communicating information. And after sketches are created, you can run really fast computations. There are some cons, of course. So they have the initial overhead of computing the sketch. They can give inexact or wrong answers. Sometimes they're a bit more complicated, but as you saw, they're not actually that much more complicated to implement. We implemented a couple. We ran out of time to implement all of them fully, but they're not that much harder to implement than the ordinary Python data structures. But the big thing is you do have to design a specific sketch for each query type. And that's one of the harder parts of using sketching is, but luckily for you, most of these sketching types are common queries people have already designed. So you just have to go online and find the right sketch type, and then you can just like plop it into Python or whatever other language you're using. I guess Rust is in these days. I'm a big fan of Rust, but plop it in, and often there will already be a library that makes use of it. And this gives you significant space and time savings at the cost of a little bit of accuracy. And with that, I think that is the end. So thank you all so much for coming to my talk. If you have any questions, just let me know. I'm also on Discord, so if you have any questions, you can feel free to ping me there. I don't actually know how to mention my Discord handle, but I'm sure that can be arranged. So, and I'll be looking out a little bit on Discord, though not spending too much time. I'm not actually participating in Sackalon, just coming here to give a workshop. So thank you all very much, and happy hacking! And let's see, how many people did I manage to keep through that whirlwind intro? Oh, okay, there's still some people who managed to stick around. So, yeah, there's a lot of cool stuff, and I went through it really quickly. Like, you could teach an entire semester class on these kinds of data structures. I mean, some people do. But you don't need all that information to like really just get started. I mean, that's the whole point of a hackathon. You don't need to know everything. You just need to know a tiny bit. And, well, then you can get started, and occasionally things break, but that's all right. Yeah, so I'll stick around. Do you have any suggestion on reading materials regarding this? That depends on what level you are. So how much math and CS have you had? So that's the real, because like there are readings on this that range anywhere from like directed at software engineers to directed at PhDs in computer science. Yeah, so there are a couple good articles actually on where are they? Let's see. Hyperlog for engineers, I think, is probably one of the better articles. Let's see. Hyperlog in practice. Oh no, that's a bit hard of an article. Where are like? Give me a moment. Let me find a couple blog posts. Oh yeah. So let's say like this one here. So they're just a number of blog posts. Like what you need to search is the names of the sketches. And so the popular ones that you'll want to look up are hyperlog and minhash, since those are super commonly used, and maybe count min and bloom filters certainly. But if you just search these things, these are all really popular topics in data engineering because people use them all the time in practice. Count min a bit less so, but hyperlog, minhash, and bloom filters like are used in nearly any super performant database system that you probably use. Like there are bloom filters under the hood of a number of database systems already. Yep, yeah, thanks for stopping by. And I guess, yeah, I'll wait a couple more minutes in case you all have questions, but I assume the next workshop is going to be starting soon. What is the next workshop? Unfortunately, I'm not sure if I can click away or if that's going to mess up things. So yeah, but yeah, so there are a ton of other cool workshops that are happening. Let's see, what is the next one? Oh, Raymond Chen is giving a talk. So I think I actually had him as a student in one of my classes. But yeah, be sure to go check out his talk. I'm not sure how to. Normally, I would just say stick around in the room for the talk, but I'm not entirely sure how that works on Hopin. So you might have to leave this room and go over into his room. So, yep. Take care, everyone. Bye. Happy hacking. Oh, yeah, sure. I am on Discord. Let's see. What is the easiest way of doing this? I think if you look, let's see. Yeah, so I am on there as Wiley Alliem. So that's my Discord link if you are trying to look me up. And you can also just Google me and send me an email. So that's probably easier since I don't check Discord super duper often for the Hack the Valley channel. But yeah, so yeah, so I am somewhere on the Hack the Valley channel somewhere. But yeah. Oh, I mean, it's just here. Like you can also just Google my name. So I'm a professor at the University of Toronto, and I'm pretty Googleable. So. Okay, now that Raymond's talk is starting, I will officially end this. If you have any questions, send me an email, or I might be hanging around the Discord, though I can't guarantee it. Maybe if you tag me, I'll show up. But yeah. Okay, bye everyone.